I guess we are live. So I have to wait for the video to start playing in the other browsers to see the chat. Blah, 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 the same routine. I guess we are. There it is. Okay. So now I just have to rearrange the windows. And it should be. There we go. My mouse will work properly. Broke it. What the hell is wrong with it? Alright, retarded mouse. Doesn't like certain pieces of paper, apparently. As a mouse pad. But, you know, it's always something. Something's always conspiring to fuck things up. Sort of. Not always. Not really a conspiracy either. What's this title bar doing on this? Yeah, I gotta work on this, whatever it is. This 10 thing. It does waste a little space here. Well, anyway, can't have everything. Link is in the description, and I think I've done everything I need to do. All right, so I thought, who knows what I mean, you know, there's the two slit thing is the thing that came up, and the fact that the talking heads of physics are all full of shit. Brian Greene this time is, you know, who I picked on, but they're all full of shit. In terms of, you know, they can't even get the premises of their own physics right in terms of describing what's really happening. And, you know, it's kind of a pitiful state. Even simple things like thinking the pattern of the two-slit experiment, which is on, off, on, off, on, off, on, off, is some kind of magic, you know, when it's about as simple a pattern as you can get. And to all these assumptions that the only thing that can make that pattern is wave interference, the simplest pattern in the universe. And we're going to say there's only one thing that could possibly create that. I mean, that's just such a catastrophic error. So this whole thing of the mistake of giving photons properties beyond polarization, you know, just a huge monumental mistake in the evolution of physics and the evolution of the knowledge base called physics. And they've just been making adjustments to try to fix that mistake ever since. But there are other mistakes, like the whole bent space thing. It doesn't really explain anything. It just puts the explanation off to some other place, and so you say, okay, well, it's in the bent space, so yeah, we can't access bent space, so we don't even have to worry about seeing that or taking a picture of it or quantizing it, because it's not even in this dimension, you know, the space-time dimension. It can create events, energy, and we don't have to account for it because it's the special dimension that did it. And that's another, you know, huge mistake. The other thing it doesn't touch is inertia. So, I mean, you have this idea of bent space and this idea that it will cause something to gain velocity because it falls into this bent space, but it doesn't really do you any good in explaining momentum or velocity. Clock surprised me. It goes off every day and it surprised me. It's a little bit late, or else the clocks are all wrong in here, but I guess the heat is the works. Maybe it's the humidity. It's making the clock run slower. It's a mechanical clock. It's, you know, 11 minutes. That is pretty poor performance. break anything here. Hardware strewn about. So no viewers. Ooh, that's a really bad sign. Yeah. Well, you know, shit happens. It is Friday morning. I blame it on Friday. Friday's fault. Yeah, fucking Friday. So yeah, so inertia. So the whole idea of something that has a maintained velocity in space doesn't do you any good in explaining how that happens, why the thing keeps moving. That's sort of a very fundamental thing, you know, to physicists. That should be one of those kind of questions where they say, "Gee, if we don't have a good answer for that one, you know, we really haven't gotten anywhere." Because that's like fundamental, right? Something's moving, and you don't have an explanation for why it's doing it. That's pretty, you know, it's pretty glaring. I mean, an explanation beyond something like, well, it has mass, and when massive things move, they tend to keep moving. Well, yeah, but why are they moving? How exactly are the little atoms inside of it moving? How are they doing that? And, you know, none of this is nothing, you know, to explain in terms of a model of the dynamic of the interior, the nuclear bits, explaining how the nuclear bits do this moving through the media or mediums. And so again, that would be a place where you just start to think about, you know, there's just not a good enough model. Their model is got too many holes in it to be a useful model, that they probably need to start over. And because their model doesn't make forces relevant to each other, doesn't, in some respects, preserve conservation. The whole idea of bent space, having a separate source of energy to move planets, sort of breaks conservation rules. I mean, just say that's the way it is. Okay, it's fine. You can just say that mass does this thing. Okay, but just to say it is, it's not an explanation. It doesn't provide any conceptual material, in my opinion. I mean, it's, to me, pretty inconceivable in the proper context of a three-dimensional model. Just doesn't really work as anything but like some kind of perpetual vacuum cleaner. You know, where does the energy for the perpetual vacuum cleaner come from? And that kind of should be the giveaway. I mean, you kind of know you can't move a planet with nothing. Space is nothing. You can't bend nothing and make planets move. It just is kind of a silly explanation. To just say it magically makes it move. It's magically attracted. It's just not a physical explanation. I mean, it's called physics, and that's not a physical explanation. It's an entirely non-physical explanation. You might as well say Tinkerbell pushes it. You might as well say leprechauns cast a spell on it. It's just, it has nothing. It provides nothing as an explanation for why something moves. And this is in the, like I said, they have all this evidence, this kind of evidence anyway, that there are these forces that are quite invisible, like light. If it wasn't for the fact that the light hits electrons in our eye, if it wasn't for the fact that that light is, that electrons are reactive, to light. So let's say electrons weren't reactive to light. Then you'd have to concede that light would exist in the universe and you'd have no way of knowing it existed. There would be this thing moving around in the universe, and you'd have to concede because you didn't have electrons, you couldn't detect it, and therefore you didn't know it existed. So light is completely dependent, and we know that the frequency is what makes the electron, the fact that an electron will absorb light is completely dependent on the frequency of the light. Certain substances are transparent to certain light of certain frequency. So it's like glass windows are opaque to ultraviolet light. I guess plastic is too, right? And that they're only letting through, the visible light, and but nothing in the blue range. And then things like, I guess it's mica, and there's some other substances that are pretty opaque to visible light. I mean, you'll get some light, but it's diffracted like hell. But it's completely transparent to ultraviolet light. So it's these electrons are completely frequency dependent, and so there's another piece of just a little bit of evidence that there could be that this force is just really a manifestation of a particular, very nuanced selectivity, and that you could imagine just subtle changes in that sensitivity that would make other things visible. So anyway, but it's that idea that there can be this massive amount of radiation. Like right now, it's hot. There's a bunch of infrared radiation, and it's completely invisible to me in the sense that I can't. My skin can feel it. I can't really sense once your skin has velocity. Okay, once it has acquired, it only feels the acceleration, the change. So it's kind of like electricity in that it needs the alternating current for there to be for the force to actually be felt. Change is noticeable, but no change is hard to notice. But that's just a nuance of our brain, the neurology. So it doesn't mean too much, as a metaphor or an example relative to the mechanical universe's blindness, and but it's just more evidence again that I can know physically that it's there, that there's this energy moving, going from one place to another, and that the energy goes from one place to another. It travels, and we know that all these forces travel at a speed. So they have another piece of evidence connecting these things. They know that gravity bent space. Why does bent space move at the same speed as light? Isn't that a little bit coincidental? That all the forces, magnetism, gravity, electricity, light, they all move at the same speed. I mean, shouldn't that say something to people looking for a physical explanation, that there's something connecting these things? So instead of doing what I would call the more logical thing, and to say the forces are like light, they ended up saying the light is like the forces. So they turned it into an electromagnetic phenomenon. They turned it into a wave. And what they should have done is turned the forces into particles. And then they could understand that maybe gravity is just light we can't see. Maybe magnetism is just light we can't see. And the irony is that light is really gravity that we can see because it has a frequency, a specific frequency. But the thing it's made out of is just gravity. The gravity came first, and all the other forces are just manifestations, perversions, distortions, manipulations, filtering of the gravity. And that is such a reachable view of the reality. I mean, it's just like I just explained it. I mean, and I explained why, because you have these pieces of evidence that connect these things, and it just, again, because now it makes inertia make sense. Because now if you think of E equals mc squared, if you think about the fact that matter isn't, to imagine matter as something that absorbs energy, converts it into something else, stores it, and then reconverts it into energy, makes matter so much more complicated. I mean, you can't really do that with the atomic model. You can't really say there's some mechanism that takes the speed of light away from the speed of light. So when light goes into an electron, by their model, somehow the speed of the light is somehow eaten. It doesn't have it anymore until it ejects the mass, the substance, into a new photon and releases again, and somehow it releases it at the proper speed. Nothing less, nothing more. It's always the right speed. It seems kind of, that's one of those, like, a little bell should go off, like intuitive wise, and just say, well, this thing is, the universe is getting simpler. That sounds like a pretty complex machine I'm making. If it every single time can absorb energy, strip it of its speed, and then recreate it and give it exactly the right speed again without ever making mistakes, no errors. It's never released a photon moving some other speed. Yeah, so that just doesn't seem sensible, reasonable. It seems more reasonable to say that a photon stays a photon when it's absorbed by an atom, or more specifically the electron, and that the speed of that fish, that thing, is still in it. It's still there. Right? You have to account for it, which means that if the school of fish is moving, then you have to account, and you're establishing that the fish can't possibly move faster than the speed of light. Well, then you kind of know that the school can't go fast. It can't add speed to one of the fish moving the speed of light. That if it's moving the speed of light inside the school in a direction, and the school is moving in the same direction, those two speeds can't add. So that somehow maybe the speed of light of that electron, of the pieces inside that electron, are what's actually moving the school. That the fish with the speed of light is what's actually moving. And as that moves through, other fish are caused to move, which means they're replaced by fish going the right way. And if you think about the fish being replaced by fish going the right way, you start to realize, well, that might be that force that this accelerating electron releases, that EMF, that electromagnetic force that is expelled in the perpendicular direction, the direction that has no use to its forward progress. It's not a coincidence that the force is released in the direction it's not accelerating in. Kind of obvious. If you were going to replace something, you would be replacing the stuff going this way if you're going that way, right? If I'm going this way towards you, what stuff do I want to get rid of? Well, the stuff going this way and that way seems the sure winner for the, gee, that stuff's not doing me any good. That stuff isn't going to get me that way. So it just seems, again, so obvious. And then you come up with an explanation for what velocity is. That velocity is a school of fish that gains fish going in the right direction and loses fish going in the wrong direction. So fish that like going this way, it keeps. And fish that like going this way, it says, see ya, we don't need you. You're not doing what we need to do, which is go this way. And that's what velocity is once you gain the acceleration of releasing the crap that's going the wrong way and replacing it with stuff going the right way, then you'll have something called velocity, because more of your fish will be going the right way. And the consequence is that eventually, if you keep gaining acceleration, moving faster and faster, it means that you're getting thinner and thinner in terms of the fish going the wrong way. So you're losing your mass in the other dimensions of this way and up and down. So if you're going that way, you're becoming less and less visible this way and this way, because those parts of your mass are being replaced by mass going the right way, by fish going the right way. And then you have velocity. You have it explained as a practical fact. You could understand that if I speed something up enough, if I take a piece of matter and I speed it up enough, that eventually it's just going to be light. I'll turn it into force with one dimension only. Light has one dimension. Light has mass in one dimension, the dimension it's moving in. It has no mass in any other dimension. It has no bits moving in any other dimension. It has no substance with any influence in any other dimension, because it's purely one-dimensional energy. And that's what you become when your velocity achieves the speed of light. You aren't matter anymore, you're force. And I would argue that obviously you will lose your material form long before you get to the speed of light. Can't say I have an equation for that yet, but we're getting there. So I figured I would work on that a little bit here, maybe. Just because I did ask somebody how much an electron weighed, and I don't know if I got a great answer, but some kind of 10 to the 10th or something, let's say. You know, quantons. So a way I would look at it, I guess, is if we say that the speed of light, let me get a clean piece of paper. All right, so the speed of light is 300 meters per second, right? 300,000 meters per second. Okay, I think that's correct. So we could say that if I had to divide that speed over a bunch of other fish, it's like I had to share my speed with them, in a sense. That I could make 300,000 fish move 1 meter in 1 second. So that's one way of looking at it, that's 300,000 fish moving 1 meter in 1 second. Spread out. And then if I was only going to be moving, say, a 100th of a meter, you know, and so I could just keep adding some zeros, so then I can get to 3 million, right? If I do it, multiply by 100, is that 3 million? Yeah. No, multiplying by 10 is 3 million. So if I divide a meter by 10, that's 10 centimeters. I'm doing anything correctly. 10 centimeters. Okay, so that would be 3 million fish could go 10 centimeters in 1 second. So it's that kind of addition when you think of what adds velocity to something like an electron. So you could argue that one photon, if let's say a photon is, let's say an electron is 3 million quanta. Well, some of the quanta, some of the fish in the school called an electron would already be going in the right direction. They'd be going in the forward velocity, so you couldn't make them go faster. So you'd have to say that the you could divide that by, you could just rule out 1/4 of the fish because they're going the right way already. So you wouldn't be making them go the right way. Exchanging is what you're really doing, but exchanging costs you a fish. Let's just say it costs you one quanta. Let's see, what's a better way to say that? Costs you an interaction, and the interactions are what exchanges the bits. So then you're tying to like a Planck element of time. So yeah, it gets kind of tricky to figure out which element's more important in this function, the time or the quanta of speed. I mean, speed is time, but the quanta is moving one bit of distance in a bit of time. And I guess figuring out what that distance is just as important. Having the Planck distance is just as important as having the Planck time. And that would be what one quanta does is one Planck constant, one Planck element of time, it goes one Planck distance. Yeah, mostly. So anyway, so you could say now that the electron could be 6 million, just because if you just get rid of if you concede that the only fish you have to move are the ones not going forward, then that would be, you would say that the ones going the wrong way you have to convert. But the trick there is the ones going the wrong way don't matter, because as your velocity increases, you're running into more fish going the wrong way, and you just use the energy coming from the field then. So those aren't fish you have to convert, because you do have to maintain your orbit thing, your structure. So the fish going the wrong way, exactly the wrong way, you have to keep, because you have to keep the balance. Because the balance is what's keeping the whole thing together, the orbit, the symmetrical, polar, the thing that makes the gravity work. I mean, I didn't give an explanation of the gravity because I've done that so many times before, but that pressure that's holding things together is dependent on the mutually cast shadows, so to speak, quote unquote. So anyway, you don't have to count, I don't think, the ones going in the wrong direction, because you're not really converting them, because those are necessary to keeping the thing together anyway. So the only ones you're really converting are the 50% of the mass. Let's say if it was a stationary object and you're accelerating it, the 50% of the mass going the wrong way. And so the more acceleration something has, the less energy, theoretically, the less mass you have to convert. So the faster something's going, the less mass it has in the wrong direction. So in some sense, you should have to apply less energy to, well, you're still converting the same number of elements. You're just doing it at a faster speed to start with. So yeah, the starting speed doesn't really matter, because all you're doing is adding the acceleration. The acceleration is always going to have the same elements. So anyway, so let's say that now we're up to, since we can double it, we'll just say we're at 50% of the fish that you're going to replace. You're only replacing 50% of the mass, and some percentage of the 50% of the mass are the only things you have to affect. So you only have to affect 50% of the mass to cause acceleration. So now we can double the size of the electron. So now we can move 6 million quanta 10 centimeters in 1 second. So now the numbers are getting bigger and bigger. But yeah, that would be, that's actually happens in electricity. These electrons don't move really fast. They move kind of slowly, actually, through the wire. Because it takes a lot of photons, theoretically, to be able to impart very fast speeds. I mean, yes, one photon is moving 6 million quanta, 10 centimeters a second. But there's a lot of electrons, and there might be a lot bigger than 6 million quanta in an electron. I mean, that's not, 10 to the 10th or whatever would be, I'm still short, 3 zeros. So, electrons could be really big, bigger than I thought they were. In terms of quantizing it relative to the energy of a photon. So anyway, the whole definition of a photon, again, that's another subject where you could just say, I don't know how exactly they got that one wrong. I mean, I don't know how their interpretation ended up so bizarrely different than my own kind of obstinate, I'd even say, visualization that just seems so rational. And maybe it's maybe there's lots of psychological reasons why I found the idea of little BBs as a description of light as intuitively sensible. I mean, I did have when I was a kid, I did have some sort of brain disorder or eye disorder or whatever you want to call it, but at night, when the lights went out, if I left my eyes open and looked into the dark, I would see little tiny little dots, little round, tiny little ball bearings of different colors, all swirling about. And, it's very coincidental. I mean, I don't know, it's just a coincidence, but it is kind of, and it's probably has, like I said, it probably has something to do with the fact that this is why this makes sense to me, is because it always was my perception. So and they moved very much like a school of fish, like swarms, and there would be like a big blob of yellow and a big blob of blue, and then they'd mix colors, and it was really quite fascinating. It was sort of my version of the traditional, sorry, my voice is fucked up, imaginary friend. It was a very comforting, peaceful thing. It was really quite, I felt privileged, because I did find out that no one else saw them. Of course, I would talk about it, and then people would say, "What are you talking about?" I'm saying, "Well, those old dots you see at night." Nobody knew what the fuck I was talking about. And so I found out they were sort of my personal friend. And so that was, but anyway, so it went away when I was about, I don't know, 7 or 8 and 9, somewhere in there. So anyway, but that's how when I heard of a photon, that was just the sensible way for me to see it, was as it's a thing, a little thing. And you have a frequency, that means there's one here, and then there's one a certain amount of time after that one, there's another one, and then a certain amount of time after that one, there's another one. And so the frequency is the distance between them. So the idea of saying photon doesn't really mean anything if you're going to make it dependent on the frequency, because you need 2 then. So a photon is really 2 showing up, at least. You need at least 2 to make a ton then. But the ton, the thing that the photon actually is at a frequency. So that's where that was always broken to me in terms of an explanation, that I never was able to convert my perception of a photon into some kind of thing that was as I did try to make them into like long dashes, but that sort of completely fell apart when you started saying, well, what about a 3-mile radio wave? I mean, how does that work? The ton is 3 miles long. I mean, that doesn't make, you can't make that make sense. So, yeah, fuck that frequency made out of anything but a distance between them. And it seemed clear that they were all the same thing, and that the only thing that made them different, the only thing that made a radio wave different than a microwave, different than an infrared, different than an ultraviolet, was the distance between them. And obviously, in the same amount of time, you could get a whole lot more X-rays would hit you than radio waves, because they're closer together. So you're getting hit by more tons. So of course it has more energy because there's more bits hitting you. Duh. By kind of obvious proportions. I mean, ultraviolet light is essentially twice as intense as infrared, because there's half the amount of distance between them. So in the same amount of time, and a consistent source, you could expect to be hit by twice as much energy if it's ultraviolet, in the sense of the tons themselves. Okay, so yeah, so getting back to the original argument, this is all this creates conservation, because now you can, once you've established this quanta, then no matter where it goes, whatever form it's in, you can always know what it is. It's a thing of the same exact mass. It has only mass in one direction. It has velocity in one direction. And so it has a oneness in that direction. And it just depends on the number of them, how much energy there is. And so you have complete conservation of the energy. Because you know that you got to count the quanta, not count meaningless stuff like frequency. Let's see how else to say that. Well, anyway, it's just that idea of conservation. It just makes the whole thing fit together, because now you can explain anything. And as I wanted to point out with the velocity thing, I mean, the simple to understand sidebar of that was the creation of time dilation, or the idea that you could understand that as the matter starts going faster and its tangential dimensions are becoming less a part of its time cycle, it's spending less time doing the other dimensions, that's essentially or effectively a form of time dilation. That means it's basically surrendering its metabolism as matter, the orbit speed, for the velocity. So as the velocity increases, the internal mechanism of the structure slows down, because there's less bits doing that, because now more bits are spending their time going and not staying doing the spinning thing. So it's like then you can use the dancing analogy, or you can even use the school of fish analogy, but the dancing analogy works, that if you're dancing and then I ask you to start moving in a direction while you're dancing, you can understand how you're going to have to dance slower, because you can't move without sacrificing what you're doing. And matter can't move without compromising what it's doing. Your matter's doing something right now. If I add extra velocity to it, it's going to have to do whatever it's doing a little bit slower, because more parts of it are going to have to do that moving. There's less workers doing the dancing and more workers doing the going. Ergo, a kind of cryogenics that is the consequence of velocity, high velocity. Yeah. So another reason to dispense with the time-space dimensional nonsense and recognize that space is nothing and time is a function. There's no space-time dimension. But all of this happens because these people didn't, they were satisfied to take Tinkerbell answers, answers that didn't answer the question. Bent space doesn't answer the questions, doesn't explain enough. It uses the very force it's explaining to illustrate as illustration. I mean, you can't really, it's that circular in a sense. I mean, it's using in its most visually meaningful example of the dimple in a sheet. It's relying on gravity to explain gravity, which is silly. And like I say, if you do three-dimensionalize it, then all you end up with is this perpetual motion machine of a perpetual pulling force. And what's that made out of? Then you start to understand that bent space is a field of energy, and there's no way to visualize where that energy is coming from because they've turned it into a pulling force, and there's no way to explain pulling. There just isn't. It's one of the facts of the universe, I think, is that there's no pull ever. Pull is always a misunderstood push. You can understand push. Push is a mechanically sensible thing, but pull really isn't. Pull requires this hook. This, you can't even see how they say it. But yeah, it's not a sensible concept where push is, and it's kind of like goes to all the stuff in the even when you get into philosophy, that there's really only one force. There's the negative. So it's like in charge, there really isn't two charges, plus and minus. There's just the minus, and everything's relative to that minus. And in life, it's just the negative sensations are really the relief from a misery of some kind, relief of a tension, relief of an aggravation is really what pleasure is. Pleasure is the absence of a negative. You can't help but be ecstatic. If I eliminate all negatives inside of you, you'll be euphoric. It's the negative is the only active impediment. However you want to write it or say it. It's the first cause, is the negative. Yeah. So, but that's how the universe is working, is this external pressure of gravity is the same pressure change subtly. Given a frequency, it's a photon. Polarized, it's magnetism. And electricity is basically just magnetism, with a catch. Magnetism as it affects electrons. Yeah. Sorry, I'm a little hungry for the negative compels me to get a little more nicotine. And such. So no comments tonight. Yeah. So anyway, somebody did leave a comment on the video that this is really an opportunity for somebody to defend Brian Greene and his silly explanation of the two-slit experiment. But regardless of that purpose, somebody left a comment about the two-slit, and that maybe it'd be a good idea if I could impose a charge on the two slits, or on the slits in the two-slit experiment. And the only catch there, well, it's not the only catch, is that the slits are small enough where it'd be hard to get a charge on them, any significant charge in atmosphere. So I guess you'd have to do it in a vacuum to first eliminate the problem of the breakdown voltage. The other problem is, I think, is that the field lines aren't really going to change. The field lines are kind of dictated, not by the, let's see, what's the way you would put this. I mean, you can't say that the strength of the charge isn't going to change the field lines, because I guess they would. But I don't know if it really is going to change their density. So it would maybe change the number. I don't even think it could do that. I'd have to think about that one. These field lines do get a little complicated, because I think they're more about, the magnetic material, the material you're using to detect the field lines, are essentially creating the field lines by establishing another interactive magnetic component in proximity to the magnets. And they're just balancing against the magnetic force of the magnet. So there are positions where there's a net neutral force, where you have just as much force pushing it away as you do pulling it towards, so to speak. So just as much push from the outside as you have push from a balance of pressure. And that's what the field lines sort of represent. That something can't really move from that position unless you push it out of that position. So once it acquires the position, it'll stay in the position because it's a neutral position. So that might have something to do with the amount of mass that ends up in that field line, how it expands. And yeah, I have to, I want to play with that some bit, because it is kind of an interesting subject. If you increase the density of the material in the field line, does it's acquiring magnetism. The iron filings would be essentially becoming magnets. They line up with the magnets that exist, and they do so in a manner that's in this neutral position, where they're angled at just the right angle, where there's an equal pressure pulling and pushing. That angle of that magnet would be exactly perpendicular. Let's see this right way. It would. It has although they draw the field lines in kind of a curved line, there's a perpendicular off any one component of the field line. And so perfectly perpendicular would be the tendency, if it had any kind of, if there was any kind of force, any kind of charge, positive charge, to move it, it would move perpendicular from that position. So that's kind of demonstrating that it's a neutral, I guess is what I'm just trying to point out. All right. So, yeah, but that would be that's probably a subject I do need to go into some more, just because field lines are interesting in terms of why they what establishes their distance from the source, and their density. Because I think theoretically there's a lot of field lines. There could be an infinite number of field lines. And it really has to do more about what you're using to detect them, is essentially creating them. So the finer your material is, maybe the more field lines you'll reveal. I really have to think about that. They draw them as if they have an intensity, like the I'm just trying to remember how they're drawn. The wider spacing is stronger. I don't think that should be correct. So they're closer together is the strength of the field line. So they draw them to illustrate the strength of the magnetism, but the drawings are just abstractions. I don't know if they're actually the field lines that iron filings will line up on. Yeah, I don't think so. Yeah, I guess I have to take two magnets of different strength and play around. Use some of these little ones, I guess, and just put 10 little ones versus 20 little ones, and something like that. Because you could fold them in half and strengthen them. I'll have to think on that one. So anyway, that's a whole different subject, really. It's not really, it's not relevant to the light and the two slit experiment. But okay, so the idea of that electrons on the surface are what's causing the diffraction, and that obviously if you change the charge on the two slits, you could theoretically change the amount of electrons that are going to interact with the light, and that you'd have more or less diffraction if there were more electrons in the field. But the question is whether there are or not more electrons, technically, in the field. The fact that you have a charge on a surface doesn't necessarily mean that it will create more electrons in the field until it's reaching the breakdown voltage, right? So it's not until the atmosphere creates a conductor that the electrons start to move into the conductor. So first there has to be the creation of the conductor, which requires the alignment of the, like for the clouds, it's the ions. And that alignment has to take place before the charge can be moved, but it still has to take place. So even having the charge doesn't necessarily mean that the atmosphere between the two charged elements is ready to break down. So you'd certainly have to at least raise the voltage near the breakdown level, and it would have to be something less than that, because obviously if you reach the breakdown level, then you won't have a charge left anymore. So obviously you can't do the two-slit experiment after a spark has been ignited, across the field. That probably isn't going to work. So yeah, that does make it a little more complicated. So it would be interesting to see the two-slit experiment done in a vacuum, which I think it has. I mean, I know they've done it with electron microscope, but that experiment has a lot of bugs in it, so I can't be sure that means anything. And again, that's being done with electrons, which are another problem. Well, I don't know if they were using the electrons to make the experiment. I don't know whether they use them in the experiment. I don't recall, but I remember it had lenses and all kinds of other crap in it, which, you know, does kind of break the game. I mean, I don't think you can do an honest two-slit experiment with lenses, because that's really causing, I mean, that's obviously diffracting the light. But I suppose it depends. I guess if you're collecting the pattern well enough, it doesn't matter. You can project it with a lens. But I guess that's the problem with doing the experiment in a very small scale, is you have to have some way of making the screen bigger. So you're kind of stuck having to lens the light. But even in a vacuum, there's still electrons, you know, and so, you know, I still think there's probably field lines that the electrons will line up on and cause the diffraction. But it might be different. So there might be subtle differences that will give an indication of a change in the pattern. I mean, theoretically, there's a lot of crap in the atmosphere. And so most of the light, you know, when we see light, the concession is that the stuff, there's a lot of stuff in the atmosphere. Okay, there's oxygen and nitrogen and all this other, there's lots of water vapor. So there's a lot of molecules, but obviously the odds of hitting one of those molecules is still pretty small, because most of the light reaches us without being distorted. But clearly when the sun shines through our atmosphere, it totally, you know, creates a tremendous amount of scatter. So a big piece, a big hunk of the light, a percentage, whatever it is, 10%, 7%, I don't know, doesn't get to the Earth's surface without being scattered, without being diffracted, and it's getting here. And so clearly just light traveling through the atmosphere to some extent is going to create some diffraction, because some of the light's just not going to get where it's going. So there's always going to be a certain amount of fuzz or haze or diffraction around the periphery of anything you look at. I mean, you could never have a perfect vision of something through an atmosphere, because every foot of atmosphere is going to degrade some percentage of the photons, and it's going to cause some slight diffractions, some major diffraction, some slight diffraction, and depending how much it's diffracted it, right, it's going to create more and more visible noise. It's going to make noise. So, and yeah, I guess it's kind of obvious that the further away something is, the less, you know, it not only gets smaller, but it gets fuzzier, because the reliability of the photons is degraded by the atmosphere. This kind of demonstrates how empty space is. That, you know, when you see the light from distant galaxies and think about the fact that it's been traveling through the universe for billions of years, and it has so little, it's been fucked with so little, that you can still get a pretty good image that the group of photons is still coherent enough to its starting position, that it's been diffracted so little, you know, that you can still resolve a pretty good image of something billions of light years away. You know, this kind of demonstrates how empty space is. That there aren't even electrons, very numerous for the photons to crash into. So anyway, that would be an interesting, I don't think I've ever seen a standard sized two-slit experiment done in a vacuum. So I think that would be an interesting experiment, just to see if it does. At minimum, it should clean up the pattern. I mean, the pattern should be a lot the line should be a lot more straight. You know, the bars between the signal between the light and the dark and the light and the dark, it should be more distinct and clear. You would expect. But it would be interesting to see if it does affect the experiment substantially in terms of reducing or increasing the amount of diffraction. I mean, it really should be doable, right? Should be able to put a light source in the vacuum. Simple enough. I mean, theoretically. I guess it wouldn't matter if you put it through glass, so you could have a bell jar, just put the slits inside the bell jar. That should work, right? Just I'll have to look that up. Two slit in a vacuum. Yeah. But again, the field lines are, I think, the population of the electrons around material substances are probably going to be there whether there's a vacuum or not. So the real problem would be is that, let's say you put the two slits inside the bell jar and then you start extracting the air. Well, the problem is that you're not going to be able to extract the electrons that are on the field lines. They're not going to be sucked out because there's not going to be any, they're on field lines. They're already in an electrically neutral spot in the first place, and pulling the atoms out isn't going to change their disposition. So in a sense, I mean, a vacuum in a sense, right, it's kind of a charge thing, right? Because to pull one atom out is to make more room for the other electrons, gives them freedom. Because the atoms don't like each other because of the shield of electrons around the outside. So it's always the electrons that make atoms resist combining. But all you need is a tiny bit for certain elements, right? They like each other once they have a little bit of momentum into each other, they overcome that resistance from the electrons and they combine quite easily. So it's this game where it's the thing closest to you, like, you know, if the electron's close, then the force against you is strong. But if I can move the electron over a little bit and have one over here and one over here, the force it's a weak force in between two electrons. And now I'm really close to the proton, and now my electrons will want to get to that proton, that kind of thing. The shadowing force, I mean, again, this is all pushing force from the gravity, but just explaining it in terms of movement. So anyway, so as you're evacuating the air, the problem is that the surfaces have their field. Like, you know, you can do this with your fingers. Just put your fingers together and you kind of see these lines form. But anyway, if they're there, the vacuum isn't going to pull them away. There's no way the vacuum can pull the electrons out of the atmosphere if they're in a neutral position in a field line. So in a sense, it wouldn't change the number of electrons around each slit. So yeah, the only thing you could gain is a sharper image by getting rid of the big pieces, the atoms and the other stuff that are in the atmosphere that are fucking up the photons. But you're not going to get rid of the field photons, I mean the field electrons that are causing the diffraction. So those field electrons would still be there. So yeah, so that won't work as an experiment. That won't do it. You'd have to neutralize the field electrons. And I don't know if you can do that, right? Because they're a material consequence. They're a consequence of the structure of all matter, I think. So all matter doesn't have a flat surface. You know, nothing has a flat surface. The surface is atoms, and the atoms have electrons, and there is a certain amount of freedom for some electrons floating on the periphery of the atoms. There's always a capacity for an atom to acquire a free electron. You know, many substances will do that, and it's just a consequence that there's still enough force coming from the proton to attract an electron, and the electrons are just a little bit too obnoxious, so they're just not going to let that free electron in, so it'll just kind of float you know, on the exterior of the solid atomic structure. So I think there's always more electrons that aren't strictly bound to atoms, but they're always in association with the atoms. They're like hanging around. they're kind of free, but they're associated. I don't know how to say that. They're weakly tied to the atoms. Very weak. So weak that we might not even be able to detect the force that holds them there. But I'm sure it's there. So anyway, so that would be part of the mechanism that creates the positive and negative, the static charge things would acquire, the tendency to establish a positive and a negative in the sense of the arrangement of the atoms and the minimum number of electrons. Let's see how to say that right. Minimum number of electrons. This charge is the acquisition of electrons, right? And electrons don't like each other, but something has to keep them from going somewhere else. And so that's the catch, is that if you had a positive right over there, why wouldn't you just go to the positive? But if there's no way to get to the positive except going all the way around, and you don't have a conductor to get there, then you can't get there. Yeah, that's partially it. But to collect charge, you really do need. It's almost like they say that the charge is created by the atoms being the electron in the atoms being on one side of the atom more than they are at the other side. But that really doesn't explain the acquisition of more charge. Well, you always have to have a certain minimum number holding the other side together. So I'm just trying to think now. And how much charge you could apply to something is dependent. I mean, you'd have to say that there's a maximum voltage that something could withstand. Maybe that's the way to put it. You can only give it a certain amount of voltage. I have never thought about that one, so it's another thing to think about, the maximum amount of voltage individual atomic structures will hold. So how much voltage can the matter hold? Because I guess you could say that it would break down internally if it had a surface charge of 1,000,000 volts, but the internal structure of the matter itself wasn't stable, then the voltage could go right through the matter, technically. The charge. I don't know. I have to think about that one. Let's see. Quantum electrodynamics already explained this. Dude, fuck you. I mean, you're just too stupid. you know, it's just such a stupid comment to make on this series of videos. Obviously, you don't want to pay any attention to the videos or the links in the videos, the channel itself, and the entire story. Quantum electrodynamics doesn't explain anything. It clearly doesn't explain the two-slit experiment. Why don't you explain single-slit diffraction, fuckhead? Single-slit interference pattern, without using the canard of Huygens. Huygens is a fake principle. They only use it for one thing, to make two photons in a single-slit experiment. That's entirely its purpose. It's a fake thing they use to contrive a fake photon, so now they can make single-slit interference, because they can make a second photon that doesn't exist. The very idea of an infinite number of mini waves. How does quantum electrodynamics explain an infinite number of mini waves? How does it do that? How can you possibly put an infinite number of mini wavelets inside a limited distance slit? Why don't you explain that, fuckhead? Yeah, well, look, I'm not going to redo all my videos. So this particular video is to explain, is a response, is giving people an opportunity to defend Brian Greene, who there's a previous video on this channel. If you go to the last video before this one on this channel, I point out how he's full of shit in describing the two-slit experiment. Yeah, I mean, obviously there's an explanation, in my opinion, for the diffraction pattern. The diffraction pattern is being caused by field lines that every piece of material substance in the universe has around it, because every piece of matter has some charge field. And the electrons on those field lines are what the photons are hitting, and they're being diffracted by specific angular amounts based on how close they are to the surface of the matter. So the closer they are to the matter, the more they diffract the light. The further away from the matter, the less they diffract the light. And ergo, the light is diffracted or spread based on the surfaces. It's just surface diffraction. By specific percentages. The light that doesn't get diffracted goes straight ahead and becomes part of the central maxima. And the light that is diffracted doesn't go straight ahead, and it goes at specific angles depending on where the field lines are. Pretty simple, I think. Light doesn't bend. Light is only changed in its direction by interacting with an electron. That's it. There's no, light can't interfere with itself. A photon can't interfere with another photon. And a photon certainly can't interfere with itself. The whole idea of photons interfering with themselves is nonsense. You can't make photons do that. No other circumstance will two photons interfere with themselves. It's only when they play this game and pretend, that there's two photons going through the slits, that they create this fake second photon. The two-slit experiment creates the fake second photon, and now they've created this fake second photon in the single slit by using this stupid canard that is Huygens. So if you're saying that quantum electrodynamics explains that, no, it doesn't. It's a big fat lie. And their equation doesn't even describe the real pattern you get in the two-slit experiment. So Here's an image. What's this magnet doing in the way? So single slit, double slit. So if you make the single slit exactly the same width as the total amount of open space in a double slit, you'll get patterns that are like this. You'll get a very rich pattern on a single slit. It'll have a central maxima that's twice as big and 8 times as bright, obviously, because all the light going through the center goes through quite easily. The double slit, you'll get the same bar pattern, except the bars will have this superimposed pattern on the pattern. So in a sense, this pattern is on, off, on, off, on, off, inside of the on, off, on, off, on, off. So it's basically 2 patterns superimposed on each other. That isn't anywhere in quantum electrodynamic math. The quantum electrodynamic math doesn't explain this diminishing of the signal going to nothing, and then the signal starting again. None of that is in their math at all. Clearly you can see that this central maxima wouldn't be bright because there's an obstacle in the center blocking the center light. So it's basically the 4-surface experiment, and this is basically the 2-surface experiment. And the surfaces are causing the diffraction of the light. But that's not how they explain the 2-slit experiment. They ignore the facts, and yeah, they pretend that something magical is happening when like I said, the same exact thing is happening in a single slit experiment. Not exactly the same, but substantially the same. Like I said, the only thing different is this. Well, first, the single slit experiment doesn't create the pattern on top of a pattern. And second, the single slit has that opening in the very middle. The middle is wide open. So obviously there's more light in the center. So that's really it. The only difference. So anyway, I put in my hour plus. We'll see if somebody shows up next 6 minutes, but otherwise I think I'll call it a day. Yeah, I guess I have to schedule these or something, but it's kind of irritating to do that. So it's just going to have to be this way until it's more popular, and then there'll be more people looking for it. And yeah, I can get an argument of some kind. Beyond quantum electrodynamics already explained this. Yeah, it's not an argument. It's a unsubstantiated declaration. Yeah. Anyway, I think I got over what I wanted to go over. And there's lots of stuff to play with. I like the velocity part. The idea that the photon goes into an electron creates a little bit of movement for the period of time it's occupied in the electron. The electron ends up like it's a school, a fish, a barracuda swims, goes into the school of fish. School of fish moves with the barracuda for a little bit, and then when the barracuda leaves, that's when the school of fish stops. And it just, yeah, it is given an acceleration, and then it's the acceleration again. When you lose acceleration, it's the same thing as gaining acceleration, the same force dynamic. So you have to give back the force that you had, that you took, so to speak. So so there's, you know, a little. First, the electron gives away a couple of fish when the barracuda goes in, and then it has to absorb a couple of fish when the barracuda goes out. So it does a little negative charge thing for the time when it's being accelerated, and then does a little positive charge thing when it's decelerated. When an electron's made of photons, so it's pretty easy for it to emit them. So if you think of an electron as a hurricane, okay, think of it as like a spiral galaxy even. And the key thing is that like a spiral galaxy, there's balance, right? There's the one arm is balanced by another arm on the other side. So very different than a solar system. So it's really not about the stuff in the center. It's really about the arms that keep the galaxy together. This arm's gravity pulls this arm's gravity, so to speak. And so it's the same thing inside an electron. The photons are balanced. And so when an electron releases a photon, it's really releasing two quanta. So it's releasing two objects at a frequency. And the frequency is dictated by the spin of the electron, or the place in the electron that these quanta happen to be. But there's all of a sudden a condition, okay, where it's gained more mass, something else went in, it's got to release some of its mass, and so it releases this one. And once it releases one, it's like if I take one arm off the galaxy, you could theoretically imagine that maybe the other arm would fly into space. But it's the same kind of thing. So once it releases this one cycles around and it flies off at the same direction. So the two of them end up going the same direction, and the period is really dictated by the time of the spin. So the faster it's spinning, that would mean ultraviolet light leaves. If it's spinning slower, that means infrared light leaves. That's the simple explanation. E equals mc squared. Matter is energy. Matter is made of tons captured in spirals. And as spirals break down, they emit energy at a frequency. And usually polarized. Yeah, well, it's even more interesting when you get to the whole, like I said, to start at the website. It starts with gravity. Gravity's where it starts, and gravity is really a mechanical, photonic kind of force, and it creates shadows. The shadows create pressure that pulls things together, straight line pressure, and photons are just a form of gravity that is at a frequency. So if you called it a graviton or a quanton, you just said that's the simplest element. Gravity doesn't have polarization. It's of all polarizations, and it doesn't come at a frequency, so it can't be detected. It doesn't have a frequency. And when gravity does have a frequency, we call it a photon. And when gravity is polarized, we call it magnetism. Polarized in one direction. But yes, it's all there, all unified in one big giant complete package of explanation. Inertia, velocity, acceleration, time dilation, gravity, magnetism, electricity, it's all there. Haven't written the electricity part, so we have to do that. I have to do a lot of writing. I don't want to do it. Just got to be so technically careful about how you explain when exactly an electron creates the magnetic EMF emission. And then you have to explain how when that enters the wire, it's pushing, quote unquote, the electrons out of the wire. And then you have to explain that that's why alternating current makes, well, there's no dark energy. There's no dark matter. It's bullshit. Completely made up mush. I mean, clearly gravity is dark energy in a sense. I mean, it's invisible energy. It's invisible light. You want to call it that. But all forces are kinetic, and so you have to get the kinetic part too. You have to kind of understand how to understand how forces interact. You have to kind of understand that when two things in kinetic world crash into each other head on, it's like they never did anything at all, because one thing will go this way and one thing will go that way. And it really doesn't matter whether they bounced off each other or they went right through each other. It's the same thing, and it's invisible. Nothing happened. There's no evidence of their collision. And so once you understand that the only thing that's really being exchanged in the universe is polarization. So now there's two things that hit each other with different polarizations. Well, now they can exchange polarizations, and that can matter. Because now the polarization that was going this way can go that way, and the polarization that was going this way can go that way, and that's a noticeable change. So that's when it gets interesting. But that's all the universe is really made out of, is it's an illusion of polarization. The actual bits go in straight lines forever. As funny as that sounds, but they really do. And the only thing that really changes is the polarization as they go through each other or by each other. And that's what can be filtered out and create an object, something solid, matter, and such. But the location is the tricky word, because there's no real location. There's just interactions. And there's points where the interactions take place, or where the polarization is exchanged, where stuff is at one place, it's all one polarization moving this way, and then all of a sudden there's a change, and then there's all stuff moving one polarization the other place. And it's only where there's a transition point that becomes some point that's noticeable. I'm not too worried about Zeno. I don't even remember, to tell you the truth, but it has something to do with how many rabbits you can put in a 10-ounce glass of, watermelon juice. I mean, all this crap that people come up with is just so, it's like that is ought gap shit. It's just so stupid. Like you can't write an is statement that's a value statement. This is stupid. So, No real paradoxes, just degrees of ignorance. No, I guess that's enough. Let's see. If everything when it occupies an equal space is at rest, and if that which is in locomotion is always occupying such a space at any moment, the flying arrow is therefore motionless. The flying arrow is therefore motionless. Well, it doesn't matter. The bits are doing the moving in the first place. So there's no thing moving. There's just, it's like a school of fish. A school of fish moves. The school of fish isn't moving. The fish inside the school of fish are moving. So locomotion is a canard. But the truth is that, again, I've just said that, is that the movement is not, it's as if you could identify polarization as a color, then you could sort of understand that something could be changing polarization, the color could keep moving, but the thing itself isn't moving, it's just the color that's moving. So, I mean, it's this color image is the same thing. This video screen, it doesn't have real movement, it's just moving colors, and the colors appear to be movement as they change. But they create the illusion of movement. Yeah. So it's just the stuff at any one location changes its polarization that appears like a change in something, but something really didn't change, just polarization changed. The stuff itself didn't change. I don't know how to say it. I mean, that's the only way I can, you know, 1:38 in the morning, that's the best you're going to get. Okay, well, I'll wait for your rephrasing, but I don't think there's any point. If anything, if everything when it occupies an equal space is at rest, I don't even know what that means, to tell you the truth. So, it occupies an equal space is at rest. In the arrow paradox, also known as whatever, Zeno states that for motion, to occur, an object must change the position which it occupies. Well, as I just pointed out, the thing itself is an illusion. The school of fish is an illusion. The fish are the thing moving. He gives an example of an arrow in flight. He states that in any one instant of time, the arrow is neither moving to where it is nor where it is not. Well, clearly you can cut time and freeze the universe. So you could say if the universe was on a clock speed like a computer, then at every clock tick there would be a position. But clearly that position comes with a potential or pointing direction. So the thing will jump, the checker will move on the board in only one direction on the next clock tick. It has to move, it can only move in one direction, whatever way the arrow is pointed. So yeah, at any one moment you could say it's frozen, but it's sort of irrelevant because we know that by the rules, it has to move in the direction that it's pointing. It cannot move to where it is not. Well, again, by that would be a breaking of physics. it will move to where it is not. It just won't do it at this particular moment, but as soon as the clock ticks again, it'll go from position A to position B, and it will now have changed its position, which is the same thing as moving. Let's see, because no time elapses for it to move there, it cannot move to where it is because it's already there. In other words, at every instant of time, there is no motion. Right, well, again, a computer is doing exactly the same thing. You could say there's no motion. There's just stuff arriving at memory locations, right? But it's the same thing. I mean, obviously, the stuff we even say it's moved to your hard drive, or it's moved here, or it's moved there. It doesn't actually move there, right? I mean, what really happens is that on a clock tick, there's an instruction, and the instructions basically take the thing fish by fish, okay, and place it in a new location. But they don't actually take the stuff out of one location and actually move the stuff in that location to another location. They just say, there's a fish at this location. I will now make a fish at this new location. So it's the same thing. Well, I'm just saying that you can break time into little pieces, but you're still not going to pretend that a computer doesn't work, and you're not going to pretend the universe doesn't work. So clearly, the fact is that the arrow is an indicator of a future potential. You can't deny the future potential will be realized eventually by some point in time. So it will eventually go to where it is not. It's just not going to go there this instant. Well, again, it's not, it's exactly what it is word games. And word games, I'm not totally opposed to playing word games, but, again, there's no paradox if you understand that there is a mechanism and there's rules. I mean, that paradox is sort of getting to velocity again, which I talked about earlier, and inertia. I mean, one could argue that what makes something move, and saying that, well, it has a velocity and it just keeps velocitying. Well, that's not much of an explanation. It doesn't really explain how it goes from here to there. Doesn't explain why it's still moving. It doesn't explain why you make it move and it keeps moving. Why does it keep moving? What's keeping it moving? But I did explain that in physics, so. Whatever, just got my first glance at the website. Looks good so far, whatever. How long is the smallest instance of time? It doesn't really matter. It just doesn't matter. I mean, wherever you make the clock speed, I'm just saying that it doesn't change the rules. So it doesn't matter. Doesn't matter. The arrow is the arrow. So it doesn't really matter because it still points to a future location. So I'm just saying it doesn't really matter whether it takes 10 billion years for it to get to that location or 10 billionth of a second for it to get to that location. The point is, it will go to that location by the rules. Yeah. Well, that whole halfway crap, it's a quantizable universe, so that breaks down. There's no half of an atom. There just isn't. It's like half of a galaxy. So the point is there's no half. You'll never be able to do that because you will break the function. So I'm just saying if you cut galaxies in half, they don't stay together. I mean, there's a limit to the size. You can't have a micro solar system. You can't have, there's different, so there's size requirements. And if you break the size requirements, you break the structure. So there is no atomic weight of 0.5. Okay, you can't have that. You can't have, there's just rules. I'm just saying, so you can't break the rules. You can't go smaller than, let's say, the photon, the ton, the quanton, the whatever, graviton. You can't go any smaller. And so there's no half the distance. Just saying that there, it's a nice thing to say that there's a half a distance, but there's a, the checkerboard breaks down. You break the matter. You break the superstructure the whole thing's made out of. You can't cut it in half. There's a point when you're on the bar, you're on the tightrope, so to speak, and a tightrope can't be split, or there's no tightrope at all. So everything just falls then. There's no mechanism to hold anything else together. So once you cut that in half, you've cut the structure in half, and there's nothing left to cut in half because the whole thing breaks. But we know from our real world example that it doesn't take an infinite amount of time to take a single step. So there's obviously not an infinite amount of distance in that single step. So all this, that word game is kind of just negated by the obvious fact that that paradox isn't something we fall into. So obviously there has to be a reason the paradox doesn't work, and the reason is that the universe isn't a fractal. It isn't anything all the way down. There's no all the way down. There's a bottom, and you hit it. So anyway. I remember the cutting steps in half thing, so I remember that Zeno paradox. I don't know, I just don't remember the other one. But yeah, maybe it's all the same thing, just rephrased, but oh, I've already been over this stuff so many times, but gravity's just, think of it as there's just a gazillion things moving the speed of light. So a million of these tons, and that's all the universe is made out of. And so they just visualize them as just arrows. And arrows going in a million different directions. Well, I'm not going to draw a bunch of arrows, but well, I guess I am because I'm drawing them. Well, there's no point in me drawing them, but you can just imagine it's a big field of a bunch of arrows going all directions. Well, you can sort of imagine that if you sat at any one point in that field, so if I just put you, like just think of a pixel on the screen, you could sort of understand that there'd be a bunch of arrows that are heading right for you out of that random field. The only ones that are going to hit you are the ones pointed at you, the straight lines coming at you. And so in a sense, it's just this perfect field of radiation pointing right at you. So there's a pressure always around you that you're getting hit by arrows, the same number coming from this way as this way, and the same coming from this way as this way, because it's all perfectly random. It's perfectly complete. And so you can imagine that if I put two objects in that field next to each other, there's going to be a problem because those two objects, this object's going to absorb some of the arrows going this way, and this object's going to absorb the arrows going this way, and in between those two objects is going to be a space, an empty space, a low pressure, because they can't go around the corner. They're straight line force. So straight line forces, like light, create shadows. And the two things will essentially create a shadow on each other. Now, it doesn't explicitly work like a shadow because it's an absorption force. You would actually absorb gravity, gain its velocity, and so it's an induction thing. But I don't want to get into the whole induction argument. You're really absorbing the velocity of the gravity, not blocking the gravity. So that's a technical difference. It needs to be understood. But I'm just saying, just for visualization, you can just sort of understand that it creates a low pressure between the two objects and they're smashed together. And that's basically a simple metaphor for that force. And so any objects around each other, that's basically the force. And it's the same thing for charge, except charge is polarized. And what do I want to say? But yeah, that's it. That's why Maxwell's equations basically work, for some elements of gravity, and some gravity equations work for some elements of electricity. It's because it's basically the same mechanics. It's an inverse square straight line force, and that's what gravity is. Oh dear, what's this crap? I don't really want to do Aristotle shit. Zeno should have assumed there's only one potential, infinities, and neither place nor time divided into indivisible parts. Well, again, there's a bottom. That's the point. His treatment became the generally accepted solution until in the late 19th century. I don't know what the change was, but the current standard treatment says Zeno was right to conclude that the runner's path contains an actual infinity of parts. Well, again, it doesn't. But he was mistaken to assume this is too many. Well, that's just silly, right? So I'm just saying it's silly to think you can traverse anything that is a something that's infinitely long. So anything that's a something that's infinitely long, you can't possibly traverse. So that would be idiotic. Well, I'm just saying it's quite obvious that you the word infinite should mean something, and what it means is you're in trouble. So, where do the arrows come from? Oh, sorry. Well, that's, who the fuck has got the answer to that question? I'm arguing with idiotic physicists who are full of shit. I mean, I'm not arguing with, I'm not giving you a God theory or something. I can't, I'm going to tell you why there's something and not nothing. Well, all right, here's my example. Okay, the universe makes nothing, right? And just makes it all day long. It just keeps making nothing. Absolute, not perfect, beautiful nothing. Just wonderful, giant sheets of nothing all day long, forever and ever. But guess what? The universe is a little tiny bit fucktarded. So once in a while, whoops, it makes a mistake and the whole thing goes wrong and it ends up with something. Oh, fuck, it made a mistake. It made something. It's like a crack in the glass. So you have like a perfect nothing glass. And it just makes an error. Every bagazillion sheets of glass, there's one that's just not quite right. And whoops, it cracks. And that's us. But I don't have, there's no way to explain, this shit. What I know is it's dumb forces. I know evolution is insanely stupid. I mean, criminally insanely stupid. I mean, it just murders things all over the place. It's criminally, insanely, homicidally, maliciously evil. So I know there's no There's nothing else to it. It's just a machine, and it's just a fucktarded machine. So yeah, it's just call it fucktarded. The universe is fucktarded. I guess I should do a video titled that. The fucktardiverse. Yeah, the fucktardiverse. I guess I have to write that down. The fucktardiverse. So instead of a multiverse, we'll have the fucktardiverse. And yeah. So I don't know why people have to do that, though. In a perfectly decent physics discussion, they have to say something. Why is there something instead of nothing? Oh, why is there rules? Well, there is. Oh, shit. I mean, you can only describe what is. You can't describe why it is. So anyway, all right, so things have died down enough that maybe I could sneak out of here. So yeah, 2 hours. That's pretty long, actually, but I think it's reasonably decent content. So let's say it was successful enough, and hopefully I can find somebody willing to argue something real in person and such. Boogaloo, yes. Probably would make a good remake. So I won't even bother making the first movie. I'll just make the second one. Yeah, the Fucktardiverse Part 2. Yeah, that'll make it even more cheesy. Let's see. This treatment employs the apparatus of calculus, which has proved its indispensability for the development of modern science. Well, I mean, come on. It's, I wouldn't go that far. I mean, calculus is just a way of cheating, right? It's like doing sloppy math. So it's averaging math. So it makes it possible for you to do a very complex equation that's very time dependent and that's always moving by just basically saying, let's just pretend things are moving a lot slower than they really are. So let's just cut this to like a 1 hour period, and then that we can understand what happens hour to hour, because we can't really understand what's happening millisecond to millisecond. So it's just averaging math, right? I mean, come on, it's just breaking everything down to an average and then making it manageable. I'm not saying actual things can't be infinite, but I guess what I'm saying is that's sort of like a paradox that creates an answer, in a sense that if it was, then we'd have the problem already, right? Because there'd be infinite space between what we're doing. There'd be infinites going down, which means they would get in the way of the physics right now. There wouldn't be a floor, right? So I'm saying the fact that we know there is a floor, that time does work, that stuff doesn't get caught in infinite delays. It doesn't take an infinite time to make one step. That sort of says that there probably isn't any maximum infinites either. So I'm just saying that it probably just takes infinite out of the equation. So you really don't have to worry about it. It's not a real concept. It's just one we are making up. So in that sense. But, that's just me saying it. It's pretty hard to play with the idea of what the exact structure is of something you can't define, because someone could say there could be an infinite amount of nothing. Well, no, there really can't be, can there? I mean, technically, nothing is nothing. You can't really have infinitely nothing. I mean, that's a redundancy, isn't it? Isn't that being redundant? Yeah, well, like I said, I don't have much. I don't think much of 20th century anything, and I don't think much of science. So, I mean, all of this gets a little bit blah blah because I don't trust scientists because obviously they've been lying about all kinds of shit. They've been obviously making stuff up to make their math work. I mean, their lensing experiments suck. This gravitational wave shit is nonsense. I mean, this black holes. I mean, they're not going to explain how you make super dense matter in the first place, and then they don't take any responsibility for trying to move something like this. It weighs 2 million suns and it's going 60 billion miles a minute. Or, that's like, well, fuck you. How exactly did it acquire all that speed? Where did it get it from? But anyway, well, I'm not saying the ceiling can't be. I'm just saying that I think there's a logical argument to make that it probably isn't. That the up is probably just like the down, and same rules apply. Um, I'm not saying that, say, a photon leaving our universe, maybe it does travel forever and ever 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 and ever. Maybe. I don't know. Yeah, I'm just saying that we know there's no infinite in between me and the target, or the arrow launcher and the target. So I'm just saying it's, blah, 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 blah. We kind of can say there's no, it's like the UFO argument, right? The intelligence in the universe and life and all that shit. It seems kind of obvious that if intelligence was something the universe created, you'd have to argue there would be civilizations in the universe that have a 1 billion year head start on us, right? They could have a 10 billion year head start on us. But let's just give them a 1 billion year head start. So our technology today plus 1 billion years added to it. You're just arguing that they would be doing something that makes some kind of noise in the universe, right? That would be pretty obvious for us to pick up. So the fact that that noise ain't out there just kind of closes the door on this intelligence thing being a function of the universe. It's not a function of the universe. Oh, quarter of a minute, he turns the light off. And the next 8 to the minute, he turns the light on again. And you can do this fucking switch each time. It's like one half. I know, you're doing the same argument again. And clearly, you're just denying the fact that the switch takes time to open and close. And that eventually, you'll be opening and closing it faster than the switch can open and close. So you can't turn the light switch on faster than the light switch can move. The light switch is limited. It can only go the speed of light, right? It can only go up or down at the speed of light. So you can only switch the light at the speed of light. So once you've cut it to the speed of light, you've already found your limitation in that you're now turning it on and off faster than the switch can turn the light on and off. So you're done. I'm just saying that there's no physical structure that you won't find the limit of it, because there's a limited speed to light and you can't violate it. So once you're doing something faster than the light is moving, then you're done. Your experiment's over. I'm just saying there's no physical structure. So unless you create an imaginary light switch, your experiment is over when you reach the mechanical limits of the switch. Thank you. I mean, not that I don't mind having to come up with explanations, but I'm just saying I'm always going to be able to find the explanation. I'm just saying it, just throwing these little puzzles at me and saying, look, here's a puzzler. I mean, it's okay, but I just mean, it's just kind of, just having somebody poking me with a stick. Well, like I said, it's only a contradiction. It's a thought experiment. If you could theoretically have a light that could only be on or off, and you had a switch that could turn it on and off at any speed. So, but otherwise, it's not a contradiction. Yay, everybody's forgetting about it. Let's all forget stuff. Yay, that's fun. Let's forget things. Oh, I remember that chick. I remember I asked her out. I said, hey, we're kind of connected, baby. And yeah, maybe we should fuck or something. She was like, I wouldn't fuck you if you're the last man on earth. I was like, whoa, whoa. Boy, I really missed there, didn't I? Oh, boy, I'd like to forget that. Let's forget that one. I'll never sleep with you in the history of time and space and shit. I remember saying that to my face. But I have subtly changing her mind now, because she's migrating towards visualizing the idea of it, finding it appealing, which is funny. So maybe I won't forget about that, because that actually might be something for the future. Well, there are circumstances where I don't really want that future. So never mind. I'm going to forget about it. Yeah, I'm going to forget about that day altogether. Just forget about it. But you really hate that, right? Because you kind of nag yourself into it and you say, hey, Gary, you've never really taken any chances. You don't you don't sit there and put your nuts on the line, and so just to do it, and you're just like, oh man, crash and burn. It's just like, oh, that hurt. Eek. And people talk like, oh, it's no big deal, but oh yeah, it's kind of a big deal. Yeah. I actually see those words come out of there. I'll never sleep with you ever in the history of the universe. Ooh, painful. I am so sick of drug talk. I mean, really. I mean, every single time somebody does a live room, some shithead. Sorry, no offense. Hey, dude, did you try shrooms? Dude. I mean, it's just so fucking, and then in a physics room, no less. I mean, they can't even, for the sake of science and physics, get their head out of the drug toilet. I mean, drugs are fucking masturbating. Okay, you want to pretend it's something else. It's some kind of special, super special ride. No, it's just jerking the fuck off. You're jerking your brain off because maybe your penis doesn't work very well, and so you have to do it the hard way. So that's your problem. But I mean, it's recreation. It's playing with yourself. It's shoving stuff up your butt. I mean, it just isn't some kind of magical thing. I mean, I just don't get you people with this fixation. I'm not against drugs, don't get me wrong. I think pot's really fun. But it's a fucking toy. That's all it is. It's a fucking toy. Ugh, Jesus. Now, everything tends to make me fall asleep eventually. Yeah, you do anything long enough, it'll make you fall asleep. Frankly, I don't even think I'd do a drug called Soma. What the hell is that? Who named that? Sounds like some kind of Arab thing, some kind of Muslim drug. I only do perfectly good American drugs. Yeah, well, you're gonna have to wait until I win it, but I'm just saying, the truth is, I'm just saying that I have outdone Einstein as a practical fact. You want to play some game? Go ahead, play a game. Okay, you haven't made a counter argument, douchebag. And you are a douchebag, right? I mean, what? I don't even know what this. What does your fucking icon mean, and what does your fucking name mean, retard? Yeah, I don't remember drugs in the Brave New World. I thought they had some kind of plague, and everybody died, and then a few people lived, and then they took an airplane, they made some super city, and then they were going to take a big rocket somewhere, and all the people said, "Oh, fuck science," and they tried to attack the rocket, but the rocket took off. Something like that. Frankly, it was a bit of a weird story. I didn't get it. Yeah, it didn't really make any sense at all. So it was Soma. I just don't remember the Soma in Brave New World. I just remember the whole. Everybody was dying of something, right? I mean, I don't remember people taking drugs. Yeah, I remember them having any good times. Uh, I'm just saying that Einstein was a smart guy. I'm like, I'm not dissing Einstein. I'm just saying that what he came up with were gimmicks. Okay, there were little three bear stories. It really wasn't very good physics. Okay, I mean, bent space is bullshit. The whole time space. I mean, connecting distance to time was reasonable. And certainly E equals MC squared right there. I mean, well, it's hard to give somebody a trophy for figuring out the obvious. I mean, it seems kind of obvious that matter was energy because, fuck, it just seemed kind of obvious that it collected it, that it must go in there, and that whatever goes in comes out. I mean, we already kind of knew that part, but I'm just saying, if Einstein would have taken his own stuff seriously and actually thought of matter as energy, you could have done a lot better. I mean, it was just, the whole idea of Einstein, thinking about traveling on a light beam. I mean, that was such flawed thinking, because you should recognize that if you're going as fast as a piece of light, your matter would be ripped to shreds. You're in the 10th grade. So it's like, what, a junior or something? I don't know if I can help a junior. Maybe you have to be a sophomore or something. Vapor pressure. Pressure is pressure, in my opinion. But I mean, obviously, vapor pressure is really about noise, right? It's about how much noise, how much loose crap there are between the atoms. And so, once you get rid of the loose stuff, then the atoms can stick together. But they can't stick together as long as there's loose stuff, heat. So, vapor pressure really is about heat pressure. They took some holidays to totally lose themselves. Yeah, I just don't remember any of that stuff. I guess I mean, maybe they're different movies. I mean, the Brave New World, right? I mean, I'm just saying there was some guy. I remember he was flying an airplane. I remember there was a plague. He cured the plague or something, and then in the future, he was living in kind of a nice place, and his daughter or something was now the scientist, and she was going to go to Planet X or something, and all the people went crazy for some dopey reason, and they were going to storm the rocket ship and stop them from going, and but they took off anyway, and all was fine. Something like that. Well, vapor and liquid, the only difference is density, right? So, you know, they're bigger molecules in liquids. Yeah, that's a good way to put it. Pressure is pressure. Yeah, there you go. That's the answer. Well, it does kind of depend, but I guess I'm just saying that usually pressure is, you know, the vacuum pressure would be gravity. You could argue that's the ether, um, and all the other pressure is that vacuum pressure converted either by frequency or polarization into what we recognize as force, and those forces obviously cause attraction and repulsion. And the idea of pressure would be that there's a repulsive force that won't allow cohesion because everything's moving too fast, so it can't combine. You know, stuff's moving too fast, it just can't do the handshake thing. You know, it's like if you're trying to save somebody in a stream and they're going by you too fast and you grab their arm, but they're going too fast and you just can't hold on. So that's sort of the problem with pressure, is that if the atoms are moving too quickly, they have too much fish in them going one direction. Yeah, they're just doing too much ricochet rabbit bullshit to be able to coalesce into a solid. So they stay vaporous until something slows them down, until something uh, causes a mitigating force to absorb their velocity. Yeah, whatever, spinach guy. There's no fucking dark matter, so go ahead, dream on. You're an idiot. I mean, I don't really have any interest in your declarative statement. So unless you have some really something called real evidence to back up your declarative statements, you can go shove them up your ass, and I'll just block you. Okay, jackass. I'm really not interested. Well, another way of saying saturation, though, is also to say that there's a maximum velocity, and there's also what's the right word I'm looking for? There's a point where you'll, if you create too much excitement, you'll break whatever binding is holding them together, or anything that's in the field. So it's almost like the breakdown voltage. You know, if your voltage goes too high, then any conductor will do. Yeah, well, boiling point's more about like an ionizing point, isn't it? I mean, that's, you know, that gets into a whole nother subject, I think. Well, I don't know if you guys want to talk about the specifics of certain compounds and pressure. I don't know if this is the place to do that. That's like a Facebook thing or something, like. Yeah, yeah, go do that in Facebook. Uh, yeah, I don't know if I'm too interested. Just saying. So anyway, it seems still hot in here for some reason. Only 83, that's not so bad. So anyway, I'm still here, and I probably shouldn't be, because I was supposed to have left. But I played Paradox games instead. I understand you're trying to be helpful and all that kind of stuff, but obviously it was a very vague question. So, I just don't know if there's the specific dynamics of the exchange of thermal entropy in, complex compounds is exactly, um, a rich area of conversation. Yeah, well, I mean, obviously, the internal pressures inside of substances are pressures that do bend around corners, technically. So it's very different than the straight line force that I'm trying to use to explain the force mechanics itself. So it's like talking about biology on the cellular level versus biology on the big organism level. Those two sciences are kind of different. So thermodynamics is an interesting subject, not saying it isn't, but obviously the physics is a little bit removed from it. You know what I'm saying? I mean, the level, you have to go down a lot of staircases before you start getting to the real physics, because the physics are going to have to do with all the electricity and magnetism that are holding the charges that are holding the atoms in association with each other. And so those forces and the amount of stuff moving is so massive in just one drop of water, that it's going to be a very complicated conversation to explain how the fields surrounding every atom have the residue of the interactions that atom has gone through in the last 15 minutes still in the local field. And that local field has a clockwise general spin, and that general spin is interacting with the counterclockwise spin of the other ions. I'm just saying, you could spend a decade, detailing the exact scientific migration of force through the thermodynamic media of a drop of water. A lot of eddies in that stream, so to speak. Well, everything relates to photons and electrons, so I'm sorry, it does apply, and it applies incredibly importantly. I mean, it's the only force is taking place. Electrons are everything, okay, when it comes to force. They're sensing the gravity, they're sensing magnetism and electricity, the polarization, the frequency. They're huge players in any atom's movement. The player is the electron. Atoms go where the electrons go, so to speak. Yeah, well, I would imagine that vapor pressure would apply to any compound, but it applies to elements also. Yeah, so, compound is a tricky word. But I'm just saying, you don't have pressure inside of something without having a bunch of loose quanta in the substance. The substance is active because the fields inside of the substance are active. And those fields are made out of photons, gravitons, or magnetons, tons. Well, it's the migration of the polarization, but again, I don't. It's just so interesting that it just keeps getting a layer deeper. You know, because there's no real movement. There's just there's just exchanging of the polarization. It's very interesting conceptually. So looks like it. Good. Excellent. So anyway, now 2.5 hours a week, long video. But most of it is good. It's only the part where I started interacting with people that it all went to hell, but no, not really. So it was okay. So anyway, till next time, and I do need participants. So if you know anybody who's a physics junkie and thinks they're a smart ass and thinks they can defend physics, you know, defend the talking heads of physics, all the bullshit that comes out of Degrassi, Tyson, and you know, Brian Greene and Sean Carroll and that other wormy nerdy cunt and the other squirmy little punk shithead and all the other little pricks of physics, Michio Kaku, all those jackasses, yeah, fuckheads, and bring them on. Yeah, you got somebody who can defend all that crap they talk. I'll rip them a new asshole. That's what I'll do. Yeah, I don't know. See, I have this old problem. I really can't schedule this shit because, you know, shit happens in the real world and you have to decide whether you're going to do something. But I, generally speaking, do it either at 12 at night or at something like 5 in the morning. But it'll be like one or the other every couple of days-ish. So you could just look and see if there's a little live thing somewhere, you know, and you'll know I'm live. But otherwise, yeah, I don't have much help for you. I guess I could send out notices or I could do something, but I just really just can't be bothered. I guess I'll have to be bothered eventually if no one continues to show up, so I don't have to be bothered, but I really don't want to be bothered. But yeah, I just hate scheduling. I just don't. I used to do that for years, and every Saturday night I'd be there every Saturday. I just hate having the burden of being in the mood, and it's just a bitch. Yeah, well, you have to go to there's the first paragraph, and then there's a more button. So obviously you have to hit the more button. And the real thing is read the first part, like the first part on gravity, and then you could probably skip the whole part about the sun moving because that part gets really convoluted because it does get complicated, right? It is kind of funny. There's all these, it's the part about the induction thing, but there's the simple part in there that to gain velocity, you have to lose your perpendicular dimensions. That part's in there, which is important. But anyway, and then the end part is the magnetism part. And I haven't written the electricity part, but the electricity part is the same as the magnetism part. It just has to do with evacuating the electrons from a conductor. And when you evacuate them, that's why AC current works, is because AC current evacuates them and lets them back in again, and evacuates them and lets them back in again. So, which is the only way it can really function. But the force basically evacuates the electrons. It gives them acceleration in both directions in the conductor, and that's why a DC current can't convey, that's why you can't use a constant magnetic field to induce electricity, is because there's no way for the migration of the electrons in one direction. But anyway, so yeah. And then there's a separate paper on inertia that's linked, and that's pretty good because that explains the time dilation thing. Molecules don't always go upward, nor is upward always relevant, i.e. in space. That is a delusion for another channel, a discussion for another channel. Well, whatever. I mean, obviously, dimensionality only has relevancy based on your orientation. So if you just concede that you have a forward, so if something isn't moving, you have to arbitrarily assign dimensions because it's equal in every dimension. So they're all equal. So it really doesn't matter what's up, down, left, right, up, and down, because they're all the same exact thing. I'm just saying most things do have an orientation. So whatever your orientation is, just then you have once you have a forward, then you have an up and down and left and right. And that's all that establishes what perpendicular is. It's perpendicular to your velocity, perpendicular to your orientation, which would be your velocity, generally speaking. Your absolute velocity. This relativity is really a pile of crap. Obviously, there's relative velocities, but you have an absolute velocity nonetheless. That's okay. It doesn't matter who you were directing it at. I chose to say something anyway. Yeah. So it doesn't really matter. But okay. I'm talking about on Earth, a liquid or solid will settle at the bottom. Well, there is a bottom when it comes to gravity, and the vapor above it, is it because of gravity? Yes, obviously. Well, I don't know. See, weight again doesn't matter when it comes to gravity, right? So, I mean, a speck of dust in the same orbit as the Earth, moving the same speed as the Earth, will stay in orbit just like the Earth. So gravity doesn't give a shit about the size of something. It just gives a shit about the the individual substance. So I go sort of back to my electron argument, or gravity is affecting the little fish. It's not affecting the big thing. So just like the little fish make the school move, the little fish are affected by the gravity, not the big thing. So gravity is a nuclear force. It's not a big thing force. It's a little thing force. The little things are creating the gravity, not the big things. I mean, the Earth's gravity is really the gravity of each of the individual quanta that make up the Earth. Let's see. Solid liquid is more dense and weighs more. Well, again, it's not about weight, but density is important. So how spread out the fish are matters. Well, and obviously the weight matters in the sense that you create a shadow on other things. How big a shadow you cast depends on your weight, right? How you're affected by a shadow is I mean, what the shadow that's cast on you is dependent on the other thing casting the shadow. So that's the catch here, is that gravity is a one-way thing. You expel gravity, and you create the gravity something else will feel, and vice versa. So your own gravity isn't felt by you. It's felt by the thing you shadow. And then obviously, if you're affecting something that you're shadowing, it can shadow you more because of the gravity you put on it. So it's like when the Earth accelerates the sun towards it, okay, by shadowing or creating a low pressure, the sun moves a little bit towards the Earth, and when it does that, it absorbs some of the gravity, and therefore casts more of a shadow on the Earth, which causes the reciprocal consequence of the Earth moving a little bit towards the sun. And so that's what I mean by induction. That gravity is really an inductive mechanism, just like magnetism and electricity. It's induced through a feedback loop. So as the things move in proximity to each other, they start to induce a stronger and stronger field between them, based on the fact that they start absorbing each other's the consequence of each other's acceleration. As I accelerate towards you, I block force that doesn't get to you now because it's caught up making me move faster. So it doesn't move as fast as it would have. The light doesn't go as fast as it would have because it's going slowly through me. So you can kind of think of it like light moving slower through a medium. And so it's like as the medium absorbs the speed of light, it means the light doesn't get to you because it's moving slowly through me. And so there's a dead period where you're not going to get hit by it. And that lack of being hit means the stuff behind you is going to go through you more, and you're going to accelerate towards me. And as you accelerate towards me, you're going to be absorbing it, and it's going to slow down. And so, so that means that I'm going to move towards you see. And so it feedback loops into its resonance, and once it hits its resonance, its maximum feedback mechanism, the maximum amount of shadow that can be cast by the amount of mass, then you reach your maximum acceleration for that distance. And then it just becomes an equation of the inverse square law in terms of your creating more and more acceleration based on how close you get. Deformation is a tricky word. Are you saying that gravity is a deformation in the electron field of matter? No, I'm saying the opposite. I'm saying the electron field of matter is a deformation of gravity. It's polarized gravity. The electron is a collection of one polarization of gravity. So it has like a galaxy. It's a plane. It's a flat thing, probably. Well, let's not even say that. It has the stuff inside of it is planier. Okay, it's polarized in one direction. So it's a collection of polarization. So whenever it releases something, it will release it at that polarization. So something can come into it with a new polarization, and it will release the polarization of the electron, and vice versa, of course, because then the electron will need to replace that wrong polarization with the right polarization, so it will absorb something with the right polarization to get rid of that wrong polarization. Oh, that would, yeah. I mean, that's, I know that's not a sufficient way to say it, but I'm just saying polarization is what is really creating what you would call the field around, the field that is or is around an electron. And polarization is what makes something relevant or irrelevant to the stuff around it. Whether or not an electron is going to be affected is dependent on polarization, the spin, and the orientation. So it's like wheels meshing, you know, two wheels going clockwise and counterclockwise. You can see that they could bite into each other, they could chew into each other. But two both going clockwise, the problem is that obviously the left side and the right side are opposite directions, so they'll bounce off of each other. So you can think of it in simple terms like that. I mean, that's not a completely accurate metaphor, but you can get the idea of why things are combinable and why things are, why they would bounce off of each other, which would be the mechanism of the field's compatibility. So what's basically creating the repulsive force between electrons is the fact that they're both expelling a polarization, okay, that they're sensitive to and that they absorb it. And so they'll move in the direction of that thing that's moving. So if polarized fish come at it, it'll eat those fish, so to speak. The school will absorb those, get rid of ones going the wrong way, and it will move in that direction. So obviously if an electron is next to me, it's producing fish of the same polarization that I absorb, it means I'm going to move away because I'm going to collect those fish. And so that's the nature of the repulsive force, is really, it's an acceleration. So it's like not a repulsive force in the sense that it's a kind of an attractive thing, in the sense that I'm like the fish the electron is producing. So if I'm an electron, I like what the electron is producing, and I keep it. And by keeping it means I'm going to move away from the electron because I kept the force it let go of. And obviously if it's letting go of it, it's going away from it. You know what I'm saying? It's like light. If I absorb the light and move in the direction of the light, I'm going to move away from the light bulb. So ironically, it moves away from what it's eating. It's as funny as that sounds. I mean, if it likes what it's eating, then it moves in the opposite direction of the source of the food, which is non-intuitive, but that's the way it works. All right, so now I think I'm done. Yeah, now we're heading towards 3 hours. Oh, it's just way too long. See, I don't want to do that long a video, and also, you know, I have to actually be awake tomorrow, so I can't be doing this shit too much like this. I got to be a little more disciplined. But I've always been bad at transitions. So anyway, thanks, and till next time, and maybe I'll try to be scheduled and shit, or I don't know, but I don't know. I don't want to. Yeah, I don't want to. Yeah, gee, that's so adult. I didn't want to. I don't like that. Well, too bad. Yes, Amanda, thank you. Oh, some mind guy was here and didn't say anything. She said something like, yes, you're correct about everything. She just say that like every 10 comments, just to make sure everybody understands that I'm correct about everything. You know, people don't know it unless somebody tells them. Yeah, so somebody has to keep saying it so they know that I am correct about everything. Mostly. Obviously, in this whole process, I have gotten some things wrong here or there for a few minutes, but I eventually corrected myself and have figured it all out. Yes, I think it was an adequate contribution in this scheme of fixing science. Somebody's got to do it, and I guess it's going to be me. Yeah. So anyway, till next time, and such and so forth, and whatnot. Thank you. Yes, exactly. I am correct about everything. I'm almost always right. Almost always. Just about. I don't know what that is. A flumange. The little yellow flamage, smiling flamage. Remember that word from Monty Python, right? Like a flamage was at Wimbledon or something. It's funny the things that stick in your head, but that really was quite bizarre, right? A flamage is, an alien flamage won Wimbledon. And you did sort of think like, wow, how did they think of that? Flamage. I never heard of flamage, and so that's why it kind of just stuck in your head. You're just saying, what the fuck is a flamage? You find out it's some kind of what? It's like some kind of hollow bready egg thing or something. It's like some sort of egg biscuit souffle thing, like a souffle biscuit. Yeah, a moth flew by. Huh, nature. Yeah, probably won't be tomorrow, but we'll see. It just kind of depends, Just maybe if I'm in the mood tomorrow, then, or if I watch a science video that's really bad, or some other shithead says something, then maybe I'll make a video just to comment about that. But I usually like to have at least like an hour's worth of content, so at least if no one shows up, I'll have something to say, so this video wouldn't be a waste of time. So that's the tricky part, right? Is that I have to make an hour's worth of content. What I should be doing is writing, and instead I'm talking, which is, sort of me evading my responsibilities here. But I do want to provoke an argument, like with a Thunderfoot or somebody. I gotta get somebody to argue with. Somebody who, is like meaningful and relevant. Yeah. Yeah. Sort of how it works. But anyway, there's no aliens. But anyway, until next time and such and so forth and whatnot. I'm gonna go this time. Stop broadcast. Yeah, I think that's what you